Hello everyone, I'm Handu from UCLA. Today I'll talk about two studies in modeling complex change in psychology. In the first study, I will use a two-stage hybrid Bayesian approach to handle cyclic data. In the second study, we'll talk about parallelized spline, which can handle more general nonlinear ghost curve model. As we can see in psychology and other social science, change usually can be nonlinear. So sometimes we may observe a spike, or some first increase, then gradually decreasing, or sometimes the change even is not S-shape. It might be cyclic, so the change might be raised, then fall, then raise again. A motivation example is from my colleagues at UCLA. They aim to investigate whether women's sexual desire fluctuate across the menstrual cycle and how this fluctuation might be influenced by relation status and partner attractiveness. A conventional way to handle this kind of cyclic data for a single person is to use a sine or cosine function. The outcome we denote as yj at time j. Mu is the average level, r is the amplitude, phi is the phase shift, and omega is the frequency. So the graph demonstrates one single trajectory, but there are multiple parameters can represent the same trajectory. For this graph, you can say it's r equal to 1, phi equal to pi, or r equal to 1, phi equal to 3 pi, or r equal to -1, phi equal to 0. So this is a multiple solution issue. So for the same data, there are infinite solutions. To solve this kind of issue, there are two possible approaches. The first approach is to just fix r to be positive and limit phi to a special range. In Bayesian, we can specify a bounded prior, or we convert the sine or cosine only function into a sine and the cosine function together without that sine coefficient. There is a one-to-one relationship between the previous equation and this current equation. The r in the previous equation is equal to r1 squared plus r2 squared and the square root for this equation. And the phi in the previous equation equal to octangle of r2 divided by r1. And we also have to pay attention to the parameter space of octangle. Octangle parameter space is very narrow, so we have to extend the parameter space back to a 2 pi space, and we use some function to link it back. And in longitudinal data analysis, it's not only one person, it's multiple person at multiple time point. So we have to introduce the multi-level model. A conventional way to handle multiple persons cyclic data is to use this kind of two-level cosine function. Now we use I to indicate the ith person. Now everyone will have an average level, everyone will have a magnitude, and everyone will have a phase shift. On the level 2 equation, we assume there is a level 2 individual covariate, which can explain why everyone has a different magnitude. This is what the my colleagues are interested in, so this model reflects their research interest. And usually we assume that the level 2 residual follow a multivector normal distribution. And without constraint, this two-level model will encounter the same multiple solution issue as in the single individual data. So there are two possible solutions. First, we can impose constraint on the fixed effect. For example, we can assume that the phase shift phi is within a specific level. However, now we have a level 2 covariate xi. So xi, even we make the constraint on r, on beta, on phi, because everyone has a different xi, everyone's ri will be different. Then this constraint is not very helpful because some person's individual effect ri can still cross the boundary. So instead, we can make constraint on the random effects by using truncated multivariate normal distribution, because previously make constraint on the fixed effect does not work. So now we make constraint on the random effect. So mathematically, this is correct, but But in my pilot simulation, I find that this approach's performance is super unstable and highly sensitive to the initial starting value. Then, how about the sine cosine combined function that we discussed previously in a single level model? If we extend to the two-level model, the level 1 equation will be similar to the one-level model. Now we have the individual covariate with, the individual covariate can influence everyone's R1i, R2i. This approach has no math challenging. It won't have the multiple solution issue. But the only problem is that the interpretation of R1, R2, beta R1, beta R2 are not as straightforward as R beta phi in the previous equation. And this equation is not the research interest to many people. No one is interested in this R1, R2, beta R1, beta R2. People are still interested in R beta phi because people want to know how individual covariate will influence the magnitude. So R beta are the primary focus to many researchers. So although this equation is easily to estimate in real data, but no one is interested in. So we still need to go back to the previous equation, which has a multiple solution issue. Then in our two-stage estimation approach, we propose first estimating the coefficient in the sine cosine function using Bayesian. So in addition to sampling the model parameter from the posterior distribution, we also sample those random effects from the posterior distribution. Then based on the sampled R1i, R2i, we can compute Ri and phi at every iteration by using those equations. Then, back to the equation we're interested in. We are interested in how those individual covariates can predict everyone's magnitude. In the previous step, we have really computed everyone's magnitude at every iteration. So what we can do is that in step 2, we can regress Ri on Xi to estimate the intercept and slope as R and beta respectively, use OLS. In this way, we can obtain the posterior distribution of R and beta. So this equation basically are the OLS solution for R and beta. However, when we use the posterior estimation and the credible interval to estimate and test R and beta, we find that the point estimate have no bias, but the coverage rates were too low. The reason is that we treat the Ri and beta I in the previous step, those estimated Ri and beta I, those random effect, as a true individual coefficient, and ignore that they contain uncertainty. So to accommodate this uncertainty in the first step, we have to do the inference using the multiple imputation standard error, which is a little bit larger than the ordinary standard error. So we can make a larger wider confidence interval. So first, we compute the standard error within each iteration. Second, we compute the average of the within imputation standard error. Then we compute the between imputation variance. Then we put the within and the between imputation standard error together as the multiple imputation standard error. And for phi and mu, we can do the same thing. We can compute phi and mu at every iteration and compute the multiple imputation standard error. Indeed, for mu, we have two options. We can use the multiple two-stage approach with multiple imputation or directly the point estimate and the credible interval. And there's no difference in our simulation. And I want to point out in 2025, Newton's group also have a similar, present a similar two-stage approach within the framework of dynamic SEM. And we conducted 4 simulation studies to evaluate the performance of the proposed algorithm. And we find that using the conventional approach, which encounter the multiple solution issue, can result in large bias and large RMSE and low coverage rate. And the performance highly depends on the true value of phi. when the true value of phi, the shift, is around the boundary pi divided over 2 or pi, the estimated R phi and beta can converge to the alternative optimization points, so which can give us a huge relative bias, negative 200%. But our proposed two-stage hybrid Bayesian approach with multiple imputation scenario can give us unbiased estimates, low RMSE, and good coverage rates. We apply this to proposed method to analyzing the motivating study, and our outcome is a sexual desire. Then the individual predictor X represent the relation status. It's a binary variable, 1 indicated in a relationship, 0 indicated single. And we find that for single participants, the average magnitude is 0.31, and the participants in a relation is estimated to have a magnitude 0.01 higher on average, with a confidence interval cover 0. Basically, it means that there's no significant difference between person in a relation and then single on their magnitude of a hormone. And in the first study, we focus more on how to handle cyclic data, so it's quite limited. In the second study, we propose parallelized spline to handle more general nonlinear model. It can be cyclic data, it can be other nonlinear data. Spline function is widely used in machine learning. Spline basically is piecewise polynomial function that satisfies suitable smoothness requirement at nodes. Nodes are the polynomial piece meet. And it's a data-driven approach, so it's unlike parametric method. So we have to specify the change trajectory ahead. Spline function finds a linear combination of locally defined basis function that best approximate the true trajectory. But to avoid overfitting, we usually smooth the spline to avoid its swing too widely, so we can have a more parsimonious model. The traditional machine learning focuses more on prediction rather than statistical inference. But in the social and behavior research, we are more interested in hypothesis testing, especially when we have multiple groups. Researchers would like to test the between-group difference on their trajectory. For example, gender difference, demographic difference, treatment versus control group. So a motivation example is that, do people with different relation status differ in sexual desire? So we examine the two types of nonlinear change in simulation. The first is the cyclic data, as in our study 1. And we also consider some like monotonic data, but they are censored, which is a ghost curve model with floor and ceiling effect. And we test the group difference in the nonlinear change at a specific time, for example, baseline, middle point, and end time point. And we specify our multi-level parallelized model as follows. It's a very complex equation. So the focal parameter here are gamma. Gamma indicate the group difference for the case basis. And there are also other important notations. Sij is a base function. Depending on which spline function we use, there can be different basis function. And the mu k is a fixed effect of the case base function for the baseline group. And the gamma k, as we just mentioned, it's a group difference for a specific base function. And we have level 2 residual, uki, and the level 1 residual, eij. And there are different basis functions within spline. For example, truncated power basis, piecewise basis, B-spline basis. And some base function experience the so-called high collinearity issue. In terms of the high collinearity issue, truncated power is the worst. Then piecewise basis is better. B-spline has the least issue in terms of highly collinearity issue because it has stronger local support. And there is a one-to-one relationship between the coefficient if we only talk about estimation, not inference. In terms of coefficient, the three bases have one-to-one correspondence. And no matter which spline function we use, the two-level model can be written in this way. Mu k is a fixed effect for the k spaces for the baseline group, and the gamma k is a group difference for the k spaces. And a paper on 2019 treat mu k and gamma k as random effect in estimation, not fixed effect. Although we usually treat gamma k and mu k as fixed effect, we treat it as random effect. By doing this, because we want to minimize the difference between uk across different k, between gamma k across different k. UKI is still between person random effect. And this group author, they give the level 2 random effect a block diagonal matrix, which means that for the first two, it's an unconstrained level 2 variance covariance matrix. But starting from the third component, there's no covariance. They're just the identity matrix. And the variance of mu k and the variance of gamma k, so which is sigma mu k, sigma gamma k, they determine the smooth level. If those variances are very small, it means that across different bases, the mu k are very similar to each other, gamma k are similar to each other. It means that we will have a smooth change trajectory. But if those variances are very large, it means that for every basis, at every cutoff point, our mu k and gamma k can change a lot. It will lead to a rough change trajectory. And we find that the model from Thuk, 2019 paper, performed very well for cyclic data, but it has low coverage rate when we have the censored data. So to address this point, we say, how about not using this block diagonal matrix? Let's use a full unstructured level 2 covariance matrix for the level 2 covariance matrix. However, and we find that by using this, the three spline bases have very similar performance. And the performance indeed are very good. And we also find that more complex change require more nodes. Nodes is how many you cut it into 5 pieces or 3 pieces. Then 5 pieces require more nodes. For better estimation, cyclic data typically require more nodes than the monotonic censored data. And as the number of nodes increase, the dimension of sigma grows. Because if you have 5 nodes, then the sigma is a 5 by 5 dimension. If it's 6 nodes, it's a 6 by 6 dimension. And the frequent estimation becomes very time consuming in our simulation. We find that for one data set, it takes more than 12 hours. So basically, no one will use this method in their real data. Then we say, how about use Bayesian? Then Bayesian estimation is much faster when we have the unstructured level 2 covariance matrix. But the critical interval is too wide. Then the coverage rate is inflated. This is because Bayesian frequency method, although their likelihood part is the same, but they use different penalty function. So Bayesian fit can be wiggler and fitting the data, try to go through the data, approximate data as good as possible. So sometimes it's fitting the data too closely, so the random noise may be triggered as signal. So we consider too much the noise. So in the end, we find that if you have the non-censored data, we still suggest that you use Thuk's method with the diagonal block matrix. It can save time and the performance is good. But if you have censored data, we would suggest that you use the unstructured level 2 covariance matrix. If the frequency estimation is too time consuming, then you can consider the Bayesian estimation. In the end, I would like to appreciate the help from my collaborator, Yang Liu, Brian, Peggy, Johnny, and Robert. Thank you, everyone.